So this is heterocyclic molecules, and we can look at aromaticity in molecules with heterocycles. And the reason why we think about these individually is because the atoms of the ring that aren't carbon, so we define a heterocycle really as any ring that contains a ring atom that is not carbon. As a heterocycle, it could be nitrogen, oxygen, that could be all sorts of interesting molecules. But the atoms that have lone pairs, the question tends to be, so does that get involved in the resonance or does it not? Right? Because that can make a big difference to the stability of the structure. So starting here with this one, so it looks a lot like benzene with one nitrogen with its lone pair. This is pyridine. Commonly shows up as a base in organic chemistry. But so if I'm looking at the electrons, if we're assuming this is planar, all the way around the ring, we have atoms that can be part of the cyclic pi system. But is it 1, 2, 3, right, aromatic, or is it 1, 2, 3, 4? Right. So the question with pyridine is always, does the lone pair count? Right? And by looking at the structure, it's hard to tell whether or not that lone pair really counts or not, unless you can see it in 3 dimensions. So pyridine, the molecule itself, is planar. So we have all these pi bonds, and since we have alternating double single bonds, all of the atoms around the ring are going to take that trigonal planar geometry, right? So the hydrogen atoms, everything is all on the same plane. And that ends up being real important, because if every atom around there has 3 bonds and is trigonal planar, that means that lone pair is going to be pointing out in that same trigonal planar sort of direction, right? So while I have my pi electrons, right, in this sort of ring above and below, I'm not going to draw the pi electrons below because it'll start to look really messy, right, which can share around in this cycle, right? So here's my cyclic pi cloud. The lone pair is put in a position where it's not really going to get involved with those, right? So just like the question about planarity leads to, okay, can the pi electrons share, right? Having that lone pair pointing out means it doesn't count, right? So the fourth one doesn't get involved in aromaticity, and anytime you see a nitrogen that's double bonded, we know it's trigonal planar, it's going to be pointing out, right? It's not going to count, right? With pyrrole, we have a different situation here. So looking at the nitrogen, it's bonded to a hydrogen. There's no double bond connected to the nitrogen. I have a lone pair and a hydrogen. So this nitrogen here is tetrahedral, right? So 1, 2, 3, does the lone pair count? In this case, if it does, that means that structure is going to be aromatic, assuming it's planar, right? I've got electrons flowing all the way around the ring, and if this lone pair counts, then it's going to work towards aromaticity. So difference is, since this nitrogen doesn't have that double bond, it's going to look a little different. And it can act as a tetrahedral molecule. And so what works here is the hydrogen will point out, the lone pair will point up into that cyclic pi system. All right, so this one can share. All right, so if you have a nitrogen with a lone pair of electrons and a hydrogen, a tetrahedral nitrogen, if it can be put into this planar position, then those electrons can share and they can count towards the pi system. It doesn't guarantee that it's aromatic, but we know we have to count those electrons. So in this case, that helps make that structure aromatic. Right, so you can get some pretty complicated aromatic heterocycles done. Right, so all the way around the ring, could this be aromatic, right? So I've got pi electrons, I've got a nitrogen with a lone pair, right? That can help share electrons. I've got pi electrons as part of this carbonyl bond, another lone pair, another pi electron. So it fulfills our criteria of having electrons shareable all the way around. All right, so that's good. But then, do we have the right number of pairs to count? So these pi systems from part of the carbonyl are outside of that ring. So they don't count towards the total number. They can count for the electron sharing. And so we've got a pi bond, we've got a lone pair, we've got another lone pair, right? It's a really strange looking but aromatic molecule here. Right, so our heterocycles, you can get a lot of variety. Examples can include oxygen atoms as well. Right, a typical oxygen in organic chemistry is going to have 2 lone pairs on it, right? 1, 2, 3, 4 pairs. If both of them count, that's not going to work towards aromaticity. This molecule wouldn't be aromatic, but it's going to take a shape similar to pyrrole here, where since this is not locked in the trigonal planar position, one set of electrons can move up and share. One set will point out kind of like pyridine. So you've got electrons shared into that pi system, and then electrons outside of it that don't. So that example would be aromatic, and our oxygen heterocycle is part of the ring. One set of electrons counts towards aromaticity, and the other one doesn't.